All right. Okay. So this one. So we studied how to evaluate moving boundary work. There are, the 5 different ways. The first one is constant volume process. When you have a constant volume process, there's no moving boundary work because you have a constant volume, the boundary is not moving, so you can assume that the moving boundary work is 0. And the second one is when you have a constant pressure process, then moving boundary work is simple as this one. And when you see no subscript, that means that you can use P1 or P2. It doesn't matter because it's a constant pressure process. P1 is the same as P2. The number 3 is constant temperature process. If you have a constant temperature process, this is the moving boundary work. If you have a polytropic process, meaning is that your real process is not one of these 3 and you cannot use this graph, then the only option is going to be polytropic process. So this is more like last resort, okay? If you cannot find, the moving boundary work in any other method, then polytropic method is the one. And the last one is a graph method. If you can, if you know how this, process looks like on this PV diagram, if you be able to calculate the area under this curve, then the area is going to be moving boundary work. But if you use this graph, you need to determine the sign of, the moving boundary work because the area is going to be always positive. The moving boundary work is going to be a positive value when it is an expansion process. It should be a negative value when it is a compression process. So once you determine this area, you need to select, the which sign should be used depending on whether it is compression or expansion. So based on that, let's solve one problem here. You can take a photocopy or the screenshot. It's going to be in your lecture recording this weekend, so you can find them. Okay. So let's solve this problem. We have a piston cylinder device. We see this piston cylinder device many times. That doesn't mean that we are studying an engine. Instead, there are 2, the simple, the systems that we study. The first one is rigid container, assuming that, the volume does not change. The other one is piston cylinder device, because piston cylinder device is a very simple geometry that can change volume without any complexity. That's why we call this piston cylinder device many times in this thermodynamics, just for its simplicity. So we have air as our system, and the mass of the system is 0.15 kilograms. Initially at 2 megapascal and 350 degrees Celsius. So we know P1 and T1. T1 is 2 megapascal and T1 is 350 degrees Celsius. And the air is first expanded isothermally to 500 kilopascal. So the first process is isothermal process. So from number 1 to number 2, this is isothermal process, which means temperature T remains constant. T1 is the same as T2. And at the final state, which is number 2, we have pressure 500 kilopascal. T2 is 500 kilopascal, and we know T2 because it's an isothermal process. T2 is 350 degrees Celsius. When you have an isothermal process, the moving boundary work can be determined by this equation. When you have an isothermal process, constant temperature process, moving boundary work is PV natural log V2 over V1. So I'm going to write this equation here. WB from process 1 to 2 is going to be PV natural log V2 over V1. Okay. Then we have a second process, and then compressed polytropically. So we have a polytropic process from 2 to 3. So there's number 3. This is polytropic process. And polytropic process looks like this. Tn to the power n is constant. Pn, PV, PVn, PV to the power n is constant. And the moving boundary work for polytropic process is given here. But this moving boundary work is between state number 1 and state number 2. This one is state number 2 to 3. So it's not P2 V2, it's going to be P3 V3 minus P2 V2 because the initial state is number 2, the final state is number 3. Okay? So it is, instead of P2 V2, it's going to be P3. Moving boundary work between 2 to 3, P3 V3 minus P2 V2 over 1 minus n. And then finally, so to the initial state. So polytropically, with a polytropic exponent 1.2. What is this polytropic exponent? This n is 1.2. To the initial pressure, what is the initial pressure? 2 megapascal. T3 is 2 megapascal. And we have a constant pressure compression process to the initial state. Constant pressure compression process to the initial pressure. P3 is the same as P1, constant pressure. When you have a constant pressure process, what is the moving boundary work? Right here, constant pressure, moving boundary work is P V2 minus V1. But this time, this one is a moving boundary work between 1 and 2. This time, 3 and 1. So, 3 and 1, P V1 minus V3. Moving boundary work between 3 to 1 is P V1 minus V3. So we want to determine the boundary work, moving boundary work for each process. So this one, this one, this one, and we are going to determine the net work of the cycle, which means that we are going to calculate the sum of these 3 to determine the net work for this cycle. Cycle means that the final process, final state is going to be the initial state. So this becomes a cycle. This cycle has 3 processes, and state number 1, 2, 3, 4. 4 becomes 1. Okay, so let's solve this problem. This one first, moving boundary work between 1 and 2. To determine this moving boundary work, what do we need to know? We need to know pressure, volume, V1 and V2. Do we know V2, V1? No. Then how can we solve this problem if you do not know V1? Do you remember any equation that we studied as V1? What was the equation that you used in exam 1? Huh? Yeah, you can use it, but that what is it called? Ideal gas equation. So we can use ideal gas equation. So the ideal gas equation, PV is nRT. Then can we use this P, P1, and for V, V2, and for this T, T3? No, you can apply this ideal gas equation not for the entire cycle, but for each state. So you can use PV-MRT only at number 1. You can use PV-MRT only at number 2. you can use PVMRT only at number 3. You cannot say P1, V3, and T2. You cannot mix them, okay? Because PVMRT, when you analyze, when you evaluate a property, you cannot evaluate a property over process. You can evaluate a property at a state, okay? So we can use PVMRT at the initial state. That means we can say P1, pressure at number 1, and V1, the volume at number 1, and M1, no, R1, no, and T1, the temperature at the initial state. Then why don't I say M1 or R1? Yeah, mass is constant. It's a closed system. So there is no M1, M2, M3. There's only one M. So that's why I don't put any subscript here. What about this R? R is a gas constant. There's only one R for air. By the way, do you remember how to determine this R? Yes? Right? No? Not yet? But that's a good time to review. Because there will be either this equation problem on Tuesday, right? So this R can be determined by R bar divided by molecular weight. And this R bar is always the same number, universal gas constant, 8.314 kilojoule per kilomole Kelvin. What about this M? Is M the same as this M? No, this lowercase m is mass. This capital M is going to be molecular weight. Then where can you find this molecular weight? From table A1. And if you want to find M for air, we can go to table A1. A1 is right here. Right? Table A1. Table A1. Air. What is the molecular weight M? 28.97. So you can put this number here. 28.97 kilogram per kilomole. So that's how you determine the gas constant R for air. But don't calculate gas constant R for air by using this equation, because air is one of the most widely used substances. So you can just memorize the number. The gas constant for air is always 0.287 kilojoule per kilogram Kelvin. You can memorize it or write it down on your formula sheet, right? Then we have R, we have pressure, 2 megapascal. So I'm going to write 2 megapascal here. No, always stick to the same unit, kilopascal. So instead of 2 megapascal, use 2000 kilopascal. So in that way, you can avoid any unit conversion. And mass is 0.15 kilograms. Temperature is what? 350 degrees Celsius. Am I right? Is this right? No. Kelvin, right? So don't make this mistake this Tuesday, right? So 350 plus 273, 623, right? Kelvin, always use Kelvin. Then you can determine V1. So if you do, V1 is 0.01341. So from here, V1 is 0.01341 from this ideal gas equation, cubic meters. What about V2? Do we know V2? No, but we know pressure and temperature. Then how can you determine V2? We can use the ideal gas equation again, this time at number 2, right? Do not apply ideal gas equation for a process, always apply this ideal gas equation at a state, not for a process. So I'm going to apply PVMRT this time for number 2. P2 V2 is M2? No, it's a closed system. Mass is constant. R2? No, there's only one R. There's only one R. P2? Yes. Then we already found this gas constant R for air, 0.287. The mass is 0.15 kilograms. Pressure is 500 kilopascal. And the temperature is again 350. So I'm going to write 350, not anymore. We know it's Kelvin, 623 Kelvin. So we have everything. You can determine the volume V2. So this V2 goes here, and the answer is 0.05364 cubic meters. That's V2. Then what about this PV? Can we use P1 V2? No, if you don't see any subscript, that means that you can either use number 1 or number 2. You can say P1 V1, you can say P2 V2, but you don't want to use P2 V1 or P1 V2. Do not mix them. You can use only one state. So this time I'm going to choose P1 V1. So what is P1? 2000. What is V1? We just found from this number. So from here, you can determine moving boundary work. The answer to this moving boundary work is 37.18 kilojoule. So this much work is required to move the piston away from the volume expansion process at a constant temperature. Any question up to here? Too fast, too slow? Any feedback? Okay, then let's determine WB between 2 and 3. So this time we know P2, V2. V2 is this number, 0.05364 cubic meters. P2 is given 500 kilopascal, and P3 is given 2 megapascal, so 2000 kilopascal. Polytropic exponent N is given 1.2. Sounds like that we have most of them, but we cannot determine WB yet because we do not know V3. So let's find V3. How? By using another ideal gas equation at state number 3. Unfortunately, you cannot do that anymore because we do not know the temperature. Then we cannot use this ideal gas equation. Do you know any other equation that has this V3? There's one. Find it somewhere here. Do you know any other equation that has V3? This one. PV to the power n is constant. What is this PV to the power n is constant? That means P1 V1 to the power n is constant. P2 V2 to the power n is constant. P3 V3 to the power n is constant. P4 V4 to the power n is constant, etc., etc., etc. And we can use this one between 2 and 3. So this is the relation. Then in this equation, do we know P2? Yes. 500. Do we know P3? Yes. 2000. Do we know N? Yes. 1.2. N 1.2. Do we know V2? Yes. This number 0.05364 cubic meters. Then can you determine V3? Now, yes. So as long as this is a polytropic process, we can use PV to the power n is constant at state number 3 and state number 2, because that is the relation between number 2 and number 3. And from here, you can determine V3. So if you do, V3 is 0.0169 cubic meters. And this one goes back to this equation, V3. Then we can determine the moving boundary work between 2 and 3. That is minus 34.86 kilojoule. Okay. Then why this one is a positive value? Why this one it has a negative sign? What does it mean in physics? Expansion, compression. Yes. Oh, n is given in the problem. Polytropic exponent of 1.2. In reality, n is not a material property that you can find from a steam table or something. N is the one that you need to determine by experiment or by calculation, and can be case by case, not a property, a material property. So depending on the gas, depending on the condition, and can be different numbers. The last process is process 3-to-1, and it is a constant pressure process. So we know the moving boundary work can be determined by this equation, and we know everything. Pressure is 2 megapascal, so that means 2000 kilopascal. V1 has been found from this equation here, 0.01341 cubic meters, and V3 has been found already here, 0.0169 cubic meters. So you can determine the moving boundary work between 3-to-1. That is minus 6.97 kilojoule. So that's how you determine the moving boundary work for each process. Once you determine the moving boundary work for each process, then you can determine the net work of the cycle. So WB net is going to be the sum of these three, 37.18 kilojoule minus 34.86 kilojoule minus 6.97 kilojoule, and it's going to be minus 4.65 kilojoule. I like this problem. This problem has most of the, the moving boundary work equations has three different processes. So if you can, it's like the final boss. When you play Super Mario, this is the total, right? So if you can solve this problem without any difficulty, then I think you're good to go in terms of moving boundary work, except the graph method. But we have a problem later, practice problem later in this chapter that we can use that graph method. So don't worry about that. We can practice all the processes. So that completes moving boundary work. Any question? Need more time to write? Okay. Yeah, not this coming Tuesday. After we finish chapter 5, then we are going to have a second exam that doesn't have answer sheet at the back. So you will see a moving boundary work for sure. What? Oh, when you have a negative sign, that means the compression process. When you have a positive sign, that means the expansion process. But when you determine the net work, the sign doesn't matter. It's a net work. So after compression, expansion, and as you can see, it's a cycle. So at last, it goes to the original location. So there's no more expansion or compression, right? But while you are doing these things, you need to, provide some work outside because you are moving these pistons back and forth. So this much work has been given by the system to the surrounding. Any question about this problem? Okay, then we have the last part of this chapter 3. The complete package, moving boundary work. I'm sorry, the energy balance equation. So let's talk about energy balance equation. So how can we determine the energy balance equation? So once we discuss that energy balance equation, we are going to solve that energy balance equation for 3 different systems. Phase change material by using table, pure gas system by using specific heat, and solid and liquid. So 3 different systems. And then that will be all for chapter 3. Then you can have a new set of homework assignments, right? So let's talk about energy balance equation. Energy balance equation. Do you remember the concept of conservation of energy principle? If you don't remember, think about the 3 hamburgers that you eat in the morning. What happens, right? So energy transfer in minus energy transfer out should be the change of energy of a system. So if you eat something, if you poop something, the change should be the weight of your system, right? Then we studied that there are 2 different energy transfers. One is heat, the other is work. So this energy transfer in can be heat or work. We use Q for heat transfer. We use W for energy transfer by work. So we have a Q in, W in. So these are energy transfer in. This one. Then what about energy transfer out? There are 2 of them. Again, Q and W. So we have heat transfer Q and energy transfer by work W is Q out, W out. What about the change of energy of a system? How do you determine the change of energy of a system? How do you determine the weight change before and after you're having a lunch in a buffet in dining hall? How you in order to measure the weight change after you hit the dining hall. You measure the weight before entering the buffet, and you measure the weight after you are full. Then calculate the difference, right? The same thing. If you want to determine the change in energy, the total energy after eating a buffet minus the total energy before entering the buffet. So E2 minus E1 is how you determine the energy change of your system. Then do you remember how to determine this total energy E? Yes, the total energy E consists of three things: internal energy U, kinetic energy, and potential energy. So internal energy U first, but we don't like this capital. We don't like this extensive properties. We like intensive properties. So we want to take mass out of it. So not this capital E, it's going to be mass times lowercase e. Mass times lowercase e1. And do you remember how to determine this E2, E1? Yes, it's going to be mass times lowercase u, that is the specific internal energy, and specific kinetic energy, velocity 2 square over 2 specific potential energy, gravity times elevation z2, minus mass times u1 plus v1 square over 2 plus gravity times elevation z1. This is what we studied in chapter 2, right? And we usually neglect kinetic energy change and potential energy change. So you can cross them out. Then what do you have? Mass times U2 minus U1. But there's one more, what we studied right before this page. Moving boundary work should be a part of total energy change. So this one, plus moving boundary work. So the energy balance equation should be Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus what? So U2 minus U1 plus moving boundary work. So this is the energy balance equation for a closed system. Oh, maybe some of you may not be very happy. It looks too long. It's too lengthy. So let's simplify it. How? First, we can assume that it's a constant volume process, like a rigid container. Then what is the moving boundary work? There's no moving boundary work. So if you have a constant volume process, the right-hand side of this energy balance equation is U2 minus U1. Okay, that's simple. And what else? If you talk about constant volume, you want to talk about another constant property. What is it? Constant pressure. If you have a constant pressure, what's going to be on the right-hand side? That's big. When you have a constant pressure, what is the moving boundary work, WB? If you have a constant pressure, what is the moving boundary work? Where is it? Constant pressure, moving boundary work is P V2 minus V1. So I'm going to write this one to replace this ugly WB. So this one, I'm going to replace this mass times U2 minus U1 plus P V2 minus V1. Oh, something bothers you. What is it? What bothers you here? Lowercase, 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 and what do you see? Extensive properties. So whenever you see these extensive properties, what do you want to do? take mass out of it. So mass times U2 minus U1 plus pressure P times mass times V2, lowercase v2 minus mass times lowercase v1. Now, what bothers you again? Huh? It's pretty long. So how can you, simplify it? We have something in common. What is it? Yes, mass. Take the mass out of the equation. Mass times U2 minus U1 plus pressure times specific volume 2 minus pressure times specific volume 1. But we are not very happy. We are not very happy. What bothers you again? Pressures, right? We see U2, U1. Okay. So this one is U at state number 1. This one is U at state number 2. This V1 is V at state number 1. This one is V state at number 2. What is this P? It should have some subscript. So I'm going, what? We know it is constant pressure process. So can I say number 1, number 2? Doesn't matter. So why don't we add number 2 here, number 1 here? No problem, because it's a constant pressure. P1 is the same as P2. Now there's a fun thing can happen. What is this one? U2 plus P2 V2. U plus PV. Do you remember what it is? We studied in this chapter last week. What is U plus PV? Last week. The week before? Yeah, last week, the week before. What is U plus PV? Whoever finds first extra credit of 0.00001. No, too low. Okay, so what is U plus PV? We learned another thermodynamic property. What is it? H, enthalpy H, extra 0.0001 point. So U2 plus P2 V2, that is H2. Oh, wait. U1 plus P1 V1, what is it? H1. So H2 minus H1 times mass. So when you have constant pressure process, the right-hand side of this ugly equation is going to be simply M times H2 minus H1. Do you remember when I introduced this enthalpy H? It has no meaning in thermodynamics, but it is convenient. This is one clue you can see it convenient. But H is more convenient when we go to chapter 4. Okay? But that we will study when we go to chapter 4. And I'm pretty sure that you will use H more and more than U, okay? So H is more widely used than U because in many cases, our thermodynamic processes are constant pressure. So H is more common. What is the word that we live? Constant volume? No. When we eat, we get fat, so it's not constant volume, but the atmospheric pressure remains almost constant. So we are living in a world when pressure P remains constant. So these are 3 options that you can use for the energy balance equation. If it is constant volume, use this one. If it is constant pressure, use this one. If it is none of these 2, use the general one, okay? So that's the variation on the right-hand side of this equation. What about left-hand side? Let's be fair. Let's talk about left-hand side. Oh, we have a Q in and Q out. What do you want to do? What we did is a simplification. So when you see Q in and Q out, What do you want to do? Yeah, you can combine them, right? Net heat transfer Q. So instead of Q in and Q out, you can say just Q, net heat transfer rate. And you see W in, W out. What do you want to do? Combine them. This big W. But there's one problem. I think you may remember, we discussed that in chapter 2. This net heat transfer Q is going to be Q in minus Q out. So no problem in mathematics. But when we determine W, net energy transfer by work, it is not W in minus W out. It is W out minus W in. So the sign between Q and 1 should be negatives. So you have two options. You can use, either of them. No problem. If you want to write this, if you want to specify whether it is incoming transfer, outgoing transfer, you can use this one. Or I want to combine, I want to, to save my ink in my pen, then you can use the second one. Okay. So that's everything about energy balance equation in chapter 3. Now, what is remaining? We just need to solve as many problems as you can together in the classroom. So when you go home, you can practice your homework assignment. So that's it. That's it. Write these down on your formula sheet, okay? And then this is what you're going to use whenever you have a closed system. And then let's solve a problem together. Refrigerant 134A at 600 kilopascal and 150 degrees Celsius is contained in a spring-loaded piston cylinder device with an initial volume of 0.3 cubic meters. Okay, we have a problem, and that is refrigerant 134. The first thing you need to, learn here is whenever you have a refrigerant, it is a phase change material. It is a phase change material. Oh, I have another version here that has all the tables that you need. R134A, refrigerant 134A, similar to water. Water and refrigerant, they are phase change material. So if you want to evaluate their properties, what you need to do? The table problem. We need to use a table. Determine the phase change process and go to appropriate table and then evaluate, find, the whatever you want. You can find it directly, or you may have to use linear interpolation. So whenever you have a thermodynamic system that you want to analyze, the first thing that you need to check is whether it is phase change material or single material such as air, oxygen, carbon dioxide. There's no phase change unless, of course, there can be phase change if you go to very extreme condition. But in general, they are considered as, the single phase material, pure gas all the time, pure liquid all the time, pure solid all the time. Then, the evaluating their properties is simple. However, whenever you have water or refrigerant R134A, then they are phase change material. And can we just use, the single material for convenience? No, we can't, because the phase change material has a lot of advantages, especially in terms of heat transfer. So we need to, to be able to analyze them. So whenever we transfer heat from here to the outside by this air conditioning unit, can we use a single material like carbon dioxide? Yes, you can. However, the cost is going to be extremely high compared to using refrigerant that can undergo phase change. Can we use carbon dioxide in my refrigerator at home for cooling? Yes, you can, but the problem is going to be you need to spend a lot of electricity to run the machine, and it's going to be expensive. So that's why we need to stick to, their phase change, because, the having a phase change it comes with lots of advantages, when in terms of heat transfer. So let's talk about this one. Spring-loaded piston cylinder device, meaning is that we have a cylinder and we have a piston. Then why do we talk about piston cylinder device so many times? Are we actually analyzing a piston cylinder device? No, we are analyzing whatever the gas inside. Then why we keep saying that, the piston and cylinder? Because this is the simplest geometry that can change the volume. That's why we use piston cylinder. It doesn't mean that this analysis is only for, some kind of engine or something. No, whenever you have a volumetric change, the simplest domain is going to be piston cylinder device. Now we have an external force, spring, loaded piston cylinder device. Initially at 600 kilopascal. We have 20 minutes. That's a lot of time, right? 600 kilopascal and temperature T1, 150 degrees Celsius. And initial volume V1, 0.3 cubic meters. The refrigerant is now cooled, so there's a cooling process. Heat is removed, Q out, until the temperature becomes minus 32. So during this process, T2 becomes minus 32 degrees Celsius. Volume V2 becomes 0.1 cubic meters. We want to determine the heat transfer and the work produced by the refrigerant during this process. So what do you want to do? If you want to determine the amount of heat transfer, the amount of energy transfer by work, what kind of equation did you study that has heat and work together? The energy balance equation. This one. Then there are three of them. So which one? Is it constant volume? No, it's a piston cylinder device. It's a constant pressure? We don't know. There's a spring, there's an external force. So maybe it's not a constant pressure process. There's no clue. Then this is the equation that we are going to use, the general one. Don't assume it's a constant volume or constant pressure unless we have a clear evidence. So I'm going to write this general energy balance equation here. Down here, Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. Then we already know that the heat transfer is Q out. Then is there Q in? Why there is no Q in? Think about the second law of thermodynamics. What is the first law of thermodynamics? This equation. What is the second law of thermodynamics? Heat transfers from a higher temperature point to a lower temperature point. So there is a heat transfer, higher temperature point to a lower temperature point. Is there a heat transfer from lower temperature point to the higher temperature point? No, it's not possible. So when there's a Q out, there cannot be Q in, right? So you can neglect Q in. Is there external work, energy transfer by work? Are we providing electricity? Are we consuming electricity? No. What about this work? That's a moving boundary work, because this spring work is going to change this tone, right? So that is related to this moving boundary work. What about the mass? Oh, we need to determine mass. We need to determine the specific internal energy U1 and specific internal energy U2. So that's what we are going to do. So let's find M first. How can we find the mass? Right. Oh, PV MRT, you cannot use it because it's a phase change material. You can use it only when you have a pure gas. So this one is a phase change material. But one thing for sure is, if you know P and T, you can analyze the state, initial state. Then what you can find? Specific volume V1. Specific volume V1 and this actual volume V1. What is the relation? The mass, right? So if you know pressure and temperature, you can determine lowercase v1, and lowercase v1 is what? Actual volume divided by mass, right? Since we already know the actual volume, 0.3 cubic meters, if you find specific volume, you get the mass. So that's our plan. So let's do it. Then we need to determine the specific volume first. How can we do that? We need to determine the phase change process and go to appropriate table to determine the specific volume. So let's do that. Oh, I don't have much space here. Since we know pressure and temperature, we can use this pressure to determine the phase change process. So I'm going to make PV diagram. PV diagram at the initial state P1, which is 600 kilopascal, and PV diagram looks like this. And to complete this PV diagram, we need to know three property values. They are T set, Vf, and Vg. Where can we find T set, Vf, Vg at this pressure? So let's find 600 kilopascal from this pressure table. 600 kilopascal is a 6 bar. So what is the temperature? T set 21.58. So this T set is 21.58 degrees Celsius. Wait. We know the temperature of our system, 150. And T set is only 21. Where is 150? Up here. So what is the phase change process? Superheated. So we have 150 degrees Celsius somewhere up here. So we have a phase change process number 5. This is 150 degrees Celsius. So if you know you have a superheat vapor, then you can go to superheat vapor table. Where is it? Here is superheat vapor table, table A12. And what is the pressure? 600.6 megapascal. What is the temperature? 150 degrees Celsius. What is the specific volume? V? 0.0555. So the specific volume is what? 0.0555. And the actual volume is 0.3. Now, can you determine the mass? Yes, you can. V3 is given. Specific volume V1 has been found from this superheat vapor table, 0.0555. Then you can determine the mass. The mass is 5.4. So this one is R134 pressure table. This one is R134 superheat vapor table. I think table 12. This one is 10 or 11. So table 2, 3, 4, 5, they are for water, and table 10, 11, 12, they are for R134A. So you have a different set of tables for different materials. And there are only two materials that we are going to study in terms of phase change. Water, R134A. Is it because that we use R134A a lot? Not necessarily. We use many different refrigerants in the world. There are R12 banned to use, R22, R134A. There are many Rs. One thing that you can do is that go to the basement of your house and then check the AC unit. And then it will give you what refrigerant that one used. Kind of fun to check, right? And sometimes, maybe some of your houses use this R134A, then you can analyze your AC machine. And in our, the appendix table, we have R12, I'm sorry, not R12, R22 and R134A. But just to be consistent in the classroom and the exam, we are going to focus on R134A. So don't worry about R12, 22, and etc. By the way, R12, which is very famous, the famous refrigerant in the world, is banned to use because it destroys what? But yeah. But some houses still use R12 when the owner bought their IC unit long time ago. And that's banned to use and banned to purchase. But if it is already there, it's going to cost a lot of money to replace. So there are people still using freon gas. Okay, so mass has been found. The mass is 5.4 kilograms from this equation. And what about U1? No problem, we can find it. 150 degrees Celsius, 6 of the kilopascal. This is U. 359.21. This is U1. 359.21 kilojoule per kilogram. What about U2? What about U2? We know the mass. So if you know the mass, you can determine specific volume, V2, which is actual volume divided by mass. Then what is the actual volume? 0.1. What is the mass? 5.4. So can you determine the specific volume at the final state? Yes, you can. What is the specific volume? 0.0185 cubic meters per kilogram. Now, you know temperature and specific volume. Can you determine specific internal energy U? Now you can, because you know how to do a table problem. You already had a very good practice time last Tuesday, right? So now we need to determine the phase change process. We know minus 32 degrees Celsius, and this is the specific volume. If you want to evaluate, if you want to analyze this final state, what do we need to do? We need to determine the phase change process. How can we assume that it's a superheat vapor? Not anymore. This is the initial state. After heat is removed, we don't know where it is, right? So we need to re-evaluate the phase change process at the end. So let's do that. We know minus 32 degrees Celsius. So at minus 32 degrees Celsius, we can make P3 diagram. It looks like this. And I need more space, right? Let's. Oh, this one, table A10. Oh, at minus 32. That's the temperature, the final temperature. So we know final temperature and specific volume. So if you know temperature and specific volume, you can make a property diagram, right? So at this temperature, minus 32 degrees Celsius, we can make PV diagram. It looks like this. And this one is P sat. This one is VF. This one is VG. So let's find P sat, V1, VF, VG. How can you find them? From this table A10, temperature table. So in this temperature table, we know there is minus 32. So this is P sat, this is VF, this is VG. So P sat is 0.77 bar, so it's going to be 77.04 kilopascal. VF is this number, 0.7172 times 10 to minus 3, and VG this number, 0.2451. So that's how you complete PV diagram. Now, we know the specific volume at the final state. It is 0.0185. So let's find the specific volume on this PV diagram. Where is the specific volume? This horizontal axis. 0.0185 is greater than VF. It's too small. It's 0.0007. But less than VG, 0.24. So the specific volume at the final state is between VF and VG, somewhere in the middle. So what is the phase change process? Saturated mixture. So this specific volume is between these two. So we have saturated mixture. So if you have a saturated mixture, how do you determine its property? We need to evaluate one more property when you have a saturated mixture. What is it? Quality X. So let's find quality X. Problem is pretty lengthy, right? That's a typical problem when you have a phase change material. So let's use a linear interpolation to determine the quality X. V is VF plus quality X times VG minus VF. Whew. So what is this V? This number, 0.0185. What about this VF? This number, 0.7172 times 10 to minus 3. VG, this number, 0.2451. VF, this number, 0.7172 times 10 to minus 3. Then, can you determine the quality X? Yes. And the quality X is 0.072766. Then, can you determine U2? Yes, if you want to determine U, specific internal energy, you can use the same linear interpolation for U. So let's use U is UF plus X times UG plus minus UF. Oh, UF. Unidentified foreign object, right? So UF is where? You can go to this table, and this is the temperature that we have won. So UF is this number, UG is this number. So I'm going to write these two numbers here. 9.47, and X has been found from here. G, 209.01. UF, 9.47. So now, can you determine U2? Yes. Where is it? 23.99 kilojoule per kilogram. So this U2 goes here. 23.99 kilojoule per kilogram. So we found the mass, we found U2, we found U1. Now, can you determine Q and W? Unfortunately, not yet. Because we have two unknowns in this equation. So we need to find WG, WB. How can you determine WB? It's a moving boundary work. So how can you determine moving boundary work? Is it constant volume? No. Is it constant pressure? No. Is it constant temperature? No. Polytropic? No. Then what is the remaining one? Graph. We have 2 minutes. I'm going to make this graph, and that will be all for today. Okay, so don't worry about that. Let me make the graph. So need more time to write here? No, right? So when you have spring-loaded piston cylinder device, this is a little important, okay? When you have a spring-loaded piston cylinder device, let's talk about force analysis. There is your 134A, your system. So what kind of forces are acting on this piston? The pressure by R134A, right? So that's the unknown pressure P. What else? Weight, yes. Weight of the piston. Which direction? This way, W. Atmospheric pressure on top of this piston. You're right. Spring force. So that's a PATM, automatic teller machine. And spring force. How do you determine spring force? K times X distance, right? So is that it? If you assume that there is no friction, then these are all the forces acting on the piston. So let's do a force analysis. The sum of forces should be what? Right. So we need to, determine the positive direction. I'm going to assume that this is the positive direction. Then P minus PATM minus KX minus W, and if you assume that the piston is here at the final state, what is the sum of forces? At the final state, the piston should be at here, right? P2. Then what is the sum of forces? Positive, going up. Negative, going down. So when it is stay there after this process, cooling process, what is the sum of forces? 0. So this should be 0. So if you write pressure, P is PATM plus KX plus W. Is this right or wrong? Must be wrong. What is wrong? What is wrong here? I think I asked the same question in chapter 1. Unit. What is the unit of this one? Newton. Force. Newton. What is the unit of this one? Newton? No. Yeah, now you see the units are different. So this is not a force. This is pressure. How can you convert this pressure into a force? Multiply by area. Then there's area. If you divide by area, then there's an area, Now, atmospheric pressure, constant. Spring constant. Is it constant or variable? It's a spring constant, so it should be constant. Area, constant. Weight, constant. Area, constant. So pressure should be some constant times X plus another constant. What kind of pressure is it if you, make PV diagram? This equation. It's gonna be a straight line. What is the initial pressure? 600 up here. 600 kilopascal. What is the initial volume? 0.3 cubic meters. What is the final volume? 0.1 cubic meters. What? Oh, I'm sorry. And so this is initial volume, initial pressure, final volume, final pressure. What is the final pressure? Number 3 is here, 77. So here, down here, 77 kilopascal. So this is the final state. This is the initial state. What is the relation between this point and this point? If you look at this equation, going up and down and connect here. No, it should be a straight line, right? Seconds. If you want to determine the moving boundary work, the area is going to be the moving boundary work that goes into this energy balance equation. So we need to continue later. This Thursday, not next Tuesday. No, we can't continue next Tuesday. We have an exam, right? So let's continue this problem next Thursday, okay? So basically, if you calculate the area, that will be WB, and the only unknown is Q, so you can determine Q and W. That's the plan.